Let's take a look now at example number 5. And this is going to be one where I'm going to ask you to try to see how far you can get on your own before watching me work through the solution. However, before you hit pause and get started, let's take a look at the integral that we have and make a few comments about it. One thing you might notice right away is that our integral here doesn't actually have any square root in it. And if you think back to all the previous examples that we've seen in this section, there's always been a square root. And so it's oftentimes easy to make the generalization that in order to do a trig sub, you must have an integral with a square root. That's not necessarily true, because you can see here, by my hint, that it would be totally possible for me to re-express the denominator of my fraction with the square root. I can almost introduce one by choice. And so I'm going to highly suggest that we start with this manipulation here. So we are actually going to work with this integral, which makes it a little bit easier to maybe see how this relates to the ideas that we've worked with before. So I'm going to ask you to start working with this integral here and to see what you can actually come up with for your substitution for x and the resulting bounds, as well as the final solution. All right, so if you've spent some time working through this, you can compare your work now to what I'm going to do here. What I could probably see is that x here could simply just be 1 times a tangent of theta. That would make dx just equal to a secant squared of theta d theta. I may not fully be aware yet of where I want theta to exist, and so my bounds might not fully be done yet either. So I'm actually going to go ahead and shift this over just a bit. But for my bounds, I can at least start to set them up. I know that my lower bound is 0, and so that would say I need the tangent of theta to be equal to 0. What theta can make that happen? I would need my upper bound to have tangent of theta result in the value of 1. And again, I'd be curious what theta can make that happen. Now again, there's infinitely many thetas that can make this the case, and so I can't just choose any of them at random. I have to think carefully about what my angle restriction is going to be and choose one out of that. Well, let's see what we come up with here. I know that my integral from 0 to 1 of this square root of x squared plus 1 all to the 4th, if I use my substitution, I'm going to get new bounds yet to be determined. In the top of my fraction, I'm going to have a secant squared of theta, put my d theta on the side. And under the fraction, I'm going to have my tangent squared theta plus 1, again, all to the 4th. So tangent squared of theta, I know is going to be equal to, or tangent squared plus 1, I know is going to be equal to secant squared of theta. And so when I absolute value, or square root, I'm going to get absolute value of secant, notice though, all to the 4th power. If I then wanted to think about bounds on that secant, I need to say, where is the secant always positive? Well, secant's always positive in, again, 1st and 4th quadrant. And so I could easily say here that my value of theta needs to be between pi over 2 and negative pi over 2. So now I can go back and update my bounds. I could say that if theta's got to be in here, which of those angles can make the tangent equal to 0? That would be 0. Which angle in there can make the tangent equal to 1? Well, that would be pi over 4. And so I have my new lower bound of 0 and my new upper bound of pi over 4. Again, because of my angle restriction, I know that in the next step, I can simplify out my absolute value bars. So I'm going to be left with a secant squared of theta in the numerator over a secant of theta in the denominator, but raised to the 4th power, or that could be rewritten as secant to the 4th. If I simplify that down a bit further, I'm going to end up with really just 1 over a secant squared of theta. Now this is a brand new integral, and I have to think about how I can tackle it. In fact, here, one of the easiest ways to tackle this would just be by doing some simple algebra. So what I'll try to do here is to just note that 1 over the secant squared is actually going to be the same thing as just writing cosine squared. And so really what I have is an integral of cosine squared from 0 to pi over 4. And again, we love integrating cosine and sine when they're squared because we know that we can just simply use our nice double angle identities, which tells us that the cosine squared of theta is the same as a half times the quantity of 1 plus 2, or 1 plus the cosine of 2 theta. So this here, very, very easy to integrate now. I know this is just going to turn into a half times theta plus a half sine 2 theta. And I just have to evaluate this from 0 to pi over 4. Again, I don't have to switch this back at all in terms of x. That's the beauty of doing the definite integral. I can just evaluate each of these directly. So, plugging in pi over 4, notice here when I double pi over 4, it's going to get me pi over 2. And then when I plug in 0, I'm going to get 0 plus a half times the sine, oops, not the sine of theta, but the sine of 0. So fortunately here, the sine of 0 is just 0, and that means the entire second term here is really just 0 as a whole. I can also see that this is going to be pi over 8 plus a quarter, because sine of pi over 2 is ultimately just going to be 1. So here again, I was able to get down to a nice final answer. I had no reason to substitute anything back in terms of x. So it's important to note that just because I don't see a square root doesn't mean that I can't use this trigonometric substitution. Now I'm also going to ask you to take a look here at part B to see if you can answer this one as well. I don't want you to evaluate this integral, but just to explain how you might approach it. What technique would you use? Hit pause again, take a couple minutes, and see if you can think about it. All right, well, it's definitely possible here that you could actually do a trig substitution. There's actually nothing wrong with doing a trig substitution here. It would be fairly complicated, right? We'd have to replace x with some stuff and simplify a bunch of stuff down, and trig subs are very, very long, especially here since this is an indefinite integral, and that means I'm going to have to do some triangle work like we had seen in the previous videos, and it just gets a little messy. However, you may note, do you have to use a trig sub here? Or could you use another type of integration technique? Well, I'm going to note that we could use a u substitution, specifically one where u is equal to 1 plus x squared, and du would then be 2x dx, or a half du is x dx. Notice actually how simple this integral would look as a result. I'd have a 1/2, a du, and a square root of u. That's an extremely simple integral to work with, way easier than doing a trig sub. And so what we want to make sure we're careful of is that we don't kind of almost get trigger happy with trig substitutions. It's not going to be helpful for us to just be trying to use trig substitutions at every opportunity. They're almost the worst integration technique. I mean, don't get me wrong, they're beautiful. They have a lot of really interesting ideas, and it's fascinating that it actually works in this way. But they're very long and tedious to use. And so if I have a simpler approach, I'm oftentimes going to take it. And so when you see radicals, don't necessarily automatically think, oh, I got to do a trig sub here. That may not be the case. Maybe a simple u sub, like we see here, could help us out and save us a whole bunch of time.